Good morning. This is session number 34, module 6, matrix analysis of plane and space frames. If you recall, we had just started the application of the conventional stiffness method to plane frames, and this is covered in the chapter on matrix analysis of plane and space frames in the book on advanced structural analysis. As you know, there are three broad methods we study. We are looking at the first of them, conventional stiffness method, and we will now look at problems where you have internal hinges in frames. We have already learned how to deal with these in beams, so it's basically the same. So I'm just showing you some of the old slides how to deal with an internal hinge. There's no transfer of bending moment across the hinge and no compatibility requirement regarding rotation. So we introduce a moment release and we introduce a clamp. So if you recall, we need to modify the element stiffness matrices. Essentially, one of those rows and columns will become full of zeros, right, corresponding to the release degree of freedom. So if you have a hinge at the start node, it's a second row and second column that gets released. Not only that, from 4 EI by L it goes to 3 EI by L, the flexural stiffness, and 6 EI by L squared becomes 3 EI by L squared, etc., etc. So we've done this earlier, and if you have hinges at both the ends, the second and fourth rows and columns will become zeros. So we are just refreshing something that we did earlier, and we also know that we need to modify the fixed end forces where you have a moment release. Essentially the fixed beam will become like a propped cantilever, and you need to modify the fixed end moments. Okay. Then finally we said that we need to deal with the fact that we will end up with a zero stiffness in corresponding to the degree of freedom where we have the moment release, because how we deal with the moment release is we are going to shift that global coordinate from active category to restrained category, right. So you don't need to inverse the KAA matrix with a zero diagonal element in it. The moment you have a release, you will have a zero diagonal element. So we conveniently pass it on to the restraint coordinate, and there it doesn't really matter. So we do this by means of an imaginary clamp. We have done this for the beam, we are just repeating this idea for a frame. So if you remember, we did this problem in the last class, portal frame with a concentrated load. The only change we now introduce is we bring in an internal hinge at a beam column joint, in this case joint C. So how do we deal with the same problem? Can we make use of some of the work we have done earlier? Can we use the same stiffness matrices? Partly yes, for AB, right. So let us go through this problem. The procedure is exactly the same as we did earlier, except that we need to make modifications for the internal hinge. So if you recall, in this slide we looked at the 6 global coordinates and the 6 restraint coordinates. I am just reproducing a slide which we covered in the last lecture, but there are going to be changes now. The changes are, firstly you have the internal hinge. So you see that hinge at C, and we are going to convert one of those degrees of freedom. Which degree of freedom? What's the number? 6. We convert it from active to restrained, and we introduce a clamp. So we do all that. Is it clear? We do that, and that degree of freedom goes to the restrained category. Nothing else changes. So how do we deal with this problem with the internal hinge? what are the changes? Do we need to make any changes for the transformation matrices? Absolutely no change, because it matters little whether the global coordinate is active or restrained. So the T1, T2, T3 are what we got earlier, there is no change. Do we need to change the fixed end forces? Yes, we do, because if you recall, at C now you have a hinge. So it's a propped cantilever you have to do. I think we know how to do this, how to calculate the fixed end moment for a propped cantilever. So we have to work this out. You are familiar with this, we have done this kind of problem earlier. So find out the fixed end forces and then work out the fixed end force vector, and then what do we do next after this? What do you do after you find the fixed end force? You have to convert to global coordinates, and after that get the net load vector or the resultant load vector. So how do we do that? We do it by Ti transpose F star. We are just repeating what we did earlier, except that the force vector is changed slightly, and we get FFA and FFR, and we get the net load vector. Okay, and you can draw a sketch showing the loads that you get. So this is identical to what we did earlier, except that now you have an internal hinge at C and those values of those forces have changed. And earlier we also had a moment applied at C, now that is released, there is no moment applied at C. And do not forget there is an indirect loading in this structure. You have dr coordinate 11, d11 will be minus 0.01 meters, because there is a support settlement of 10 mm at D, right, exactly as we had earlier. Then we need to generate the element and structure stiffness matrices. What changes do we need to do now? For element 1, any change? No. So you are right, we need to bring changes only for elements 2 and 3. Can you write them down? Can you write down the stiffness matrices for elements 2 and 3? For element 2, the end node has a hinge. So it will broadly take this shape, right. You have EA by L for your axial degree of freedom, and you will find that for the element 2 the 6th degree of freedom, that means the 6th row and the 6th column will become made up of zeros, right, and you need to modify the 4 EI by L to 3 EI by L and so on. Okay, and for the third element also, because our start node is at D, for the third element also the last row and the last column will become 0. Can I proceed? This is, you need to go through the book and see this example in greater detail. I am just repeating because we can't possibly solve these matrices in class, you need to solve them by yourself. Then how, and we have to assemble the structure stiffness matrix exactly the way we did in the last class. I have explained this earlier. So you get KAA, but note KAA now has a size 5 by 5, without the internal hinge it was 6 by 6, and then KAR and KRR can be worked out, and please note KRR will be now having a size 7 by 7. Okay, that is it. Then you solve for the unknown equations, the method is the same, and you will notice that the deflections have increased substantially compared to the previous problem. Now you have a sway of 23.4 mm, that's how you interpret the dA vector. D1 is a sway you get at B, which is shown in yellow, and D4 is a sway you get at C. Okay. Can you see something about the behavior of DC? What does it look like? It is a cantilever. Okay. So maybe there is a shortcut way of getting that deflection. We will see that. Okay. So it is good to understand behavior by interpreting the results that you get. Then you find the support reactions in exactly the same way. The second equation you solve, you can write down your support reactions. You should check your equilibrium. All these steps are identical to what we did earlier. What is the last step? Member and forces. Again, the method is the same. Draw, you find out for the 3 elements and you draw the free body diagram. And what do you do next? Well, the most important diagram for a frame or a beam is the bending moment diagram, but you can draw all the diagrams. So let us just draw the bending moment diagram. And you will see very nicely that at C there is a 0 moment, because that is exactly where the internal hinge is located. And it is here that you can interpret, you can clearly see CD acts like a cantilever as we mentioned earlier. So there is only one load. If you isolate CD as a cantilever, you have a vertical load which does not cause bending, and you have a lateral load. What is a lateral load? 18.545, and you know the formula PL cube by 3I. You plug it in, you get exactly the same answer that we got the hard way, 23.44. These are small checks you need to do, and as an engineer you should always be suspicious of the results that you get from a software. You need to check with your intuition and some thumb rule calculations to validate your solution. Is it clear? So you will find that almost everybody knows how to, practicing engineers know how to use softwares, but interpretation of results is not everybody's cup of tea. That is the difference between a really good engineer and a not so good engineer. You should be able to interpret, you should detect errors, then you have to go back to your input and correct them. Okay. Dealing with hinged and guided fixed supports, exactly similar to what we did for beams. You have to release some degrees of freedom. So let us take another frame problem. This is a bent frame. Remember we did this frame earlier by slope deflection moment distribution method, but here you will get slightly different answers. Why do you get different answers? Yeah, because here we are doing it more accurately. We are including axial deformations, which we did not have earlier in the slope deflection and moment distribution method. So how do we deal with this problem? What is the degree of kinematic indeterminacy?
2.
How many active degrees of freedom we have in the conventional stiffness method where we do not take any shortcuts? At A, how many active degrees of freedom do we have? 1. At B, 3. At C, 3. At D,
1.
It adds up to how many restraint? 4. Okay. The method of analysis is identical to the previous problem, except that here luckily we do not have any support settlements. Also we are going to use a slightly different technique of generating the stiffness matrix and the fixed end force vector. We will use the TD instead of the TI. I want you to recall the difference between using TD and TI. TD is a displacement transformation matrix. It has the big advantage of you not worrying about the slotting. You don't, but it has a disadvantage in terms of storage and programming. What is the disadvantage? Yeah, you will have to deal with larger matrices, but for problems like this it does not make too much of a difference. You understand? Let us say you had a multi-storied building and you had say 100 degrees of freedom, then your TD matrix for even a plane frame element will be 6 by 100. That is very unwieldy. But if it is TI matrix, the conventional, it will remain 6 by 6 for every element, but then you have to worry about the slotting, the linking global coordinates. So we did one problem of that variety. Let us do another problem using TD, and otherwise the method is the same. So we have as you rightly pointed out, we have 8 active degrees of freedom. I have marked them there in green color, and you have 4 restrained degrees of freedom. You can identify your start nodes and end nodes for the 3 elements. You could draw the 3 elements separately, but or you could choose to draw a typical element and you can generate the matrix. Now the TI matrix and the TD matrix actually are similar, except that the size changes. So we are familiar with the TI matrix. You have to still rope in the cos theta, sin theta, sin theta and 1. So the method is the same, only thing you have to do it with your eyes open and fill up these matrices. And it is convenient to separate out the active degrees of freedom from the restraint. So actually the TD matrix for each element will have a size 6 into 12, which you can partition into 6 into 8 for TDA, active degrees of freedom, and 6 into 4 for restrained degrees of freedom. And most of these elements in the matrix will be zeros, except where you have a degree of freedom which is active. Let us see, take the first column in these 2 matrices for TD1 and TD2. The first column actually corresponds to D1 equal to 1. If you apply D1 equal to 1, it is going to affect elements 1 and 2, right, and it is at the tail end of element 1 and at the beginning of element 2. So basically you have to use these transformation matrices and fill up at the appropriate column. You see the tail end gets filled in element 1 and the start end gets filled in the element 2. It is only 1. Is it clear? I hope you know how to fill up this. This is actually similar to what you would get if you did the TI formulation, except that you have to keep track. Now I have written on the top row, I have written 1, 2, 3, 4 all the way to 12, but you needn't do that in this case. It is obvious, it has to be a sequential form from 1 to 12. Is it clear? I hope you know how to do this. We have done it for a truss, we have done it for a beam. It is no big deal to extend that to a plane frame. Okay. So similarly for the third element you can fill up. Now the fixed end forces, very easy to calculate. In this case, of the 3 elements only the second element is loaded. It has a UDL, so you can find the end moments and the vertical forces, write it in a vector form. So you have F2 star F having that non-zero vector, whereas F1 star and F3 star will be null vectors because there is no load in those 2 elements. Clear? What do you do next? You convert it to, you want to get it for the whole structure, right? You want the FFA and FFR vectors. How do you do that? TD transpose. So that contragradient principle works, and you can sum up do 1 element at a time and sum it up for the 3 elements, and this is something you can work out for all the elements. You get FFA and FFR. You need not write down those numbers 1, 2, 3, 4 all the way to 12 because it is obvious. Okay, those numbers you need to do when you do the TI matrix. When you do TD, it has to fall into this numbering scheme. Is it clear? So you get FFA and FFR, and what do you do next? You have got the load vector. What do you do next? Right, you can draw a sketch. Look at this. This is your resultant load vector. FA is equal to FFA minus FFR. Sorry, FA minus FFA. FA is a null vector because there are no nodal loads in this particular problem. You had only a UDL, and so FFA is given there. Put a negative sign to it and interpret those results. You will find that the original problem had a UDL. What you are having here will give you exactly the same same active displacements, the same dA vector, the same deflections at B and C, vertical and horizontal, and the same rotations at B and C, okay, and at A and D, okay, because you have arrested you have to superimpose these results with the results that you get in the primary structure when you have that UDL, okay. So next you get the element and structure stiffness matrices, standard formulation for a plane frame element, right, you just have to plug in the values of EA by L, EI by L, and it all falls into place. Generate this for all the 3 elements. What do you do next? You have to generate the structure stiffness matrix. How do you do that? TD transpose K star TD, which you can do it in 2 stages. You can first do K star TD and then do the TD transpose, or vice versa. So it's best to program all this and let MATLAB do it. Just check after you get the results that you have a symmetric matrix and that your diagonal elements are all positive, and you will get some null, some zeros somewhere. If you number it more intelligently, it will fall into a nice banded matrix with minimum half band width for convenience in storage and solution, okay. So I hope up to this stage you know how to do it. If you write the full K matrix, you can't fit it into that slide because the size is 12 by 12. So it makes sense to do it KAA, KAR, KRA, KRR. Even here it helps to draw partitions as we have done it here, because 1, 2, 3 refers to the joint B. So I have drawn a partition for that. 4, 5, 6 refers to the joint C, and the last 2 refer to the rotation coordinates at A and D. Is it clear? So you must have your own system of identifying for convenience, because you need to interpret and you need to know why those zeros are where they are. They should make some kind of sense, okay. Next, so you generate all your matrices. KRR is 4 by 4 and KAA is 8 by 8. Then you solve this. Here there are no support settlements. Solve these 2 equations. First you find the deflections. When you look at that kind of deflection vector, really you can make sense mostly only of translations, okay, and the order of magnitude of the translations should make some sense in a real structure. So I marked them in yellow color, the ones that are significant. The ones that are almost 0, I have not marked them, and you have to draw a sketch, okay. So a sketch would look like this. So imagine you have this 2 hinged frame, bent frame with a UDL on BC. This is how it is going to deflect, and the deflections are very small, 0.093 mm to the right, that is a sway at B, and a vertical deflection of 0.278 mm, which is extremely small, okay. Right, so you have got this, and then you can find your support reaction solving the second equation, interpret those results, check equilibrium. Well, the least you can do is check force equilibrium. So sigma Fy should add up to 0, those 2 vertical reactions should add up to the total load of 120 kilonewton, and the horizontal reactions must cancel out, right. So it makes sense. Next, last step, find the member forces by using the TD matrix, and draw the free body diagrams and draw the bending moment diagram, draw the shear force, axial force diagram and shear force diagram. All this can be done, and compare these results with the results we got earlier by the slope deflection method, or slope deflection method, not moment distribution, because moment distribution is not good when you have sway. You will find that they are almost identical. this is more accurate because you are accounting for axial deformation. We will do the same problem by the reduced element stiffness method, where we ignore axial deformations and compare the results. Okay, here is one last problem, a really interesting problem. Remember at the end of the last class we also said let us look at temperature loading. This is more tricky because the legs are inclined. So the same frame, let us do this slowly so that you get it. Same frame with sloping legs, we are now talking of a fall in temperature, okay, by 40 degrees Celsius, coefficient of thermal expansion is given. How do you solve this problem? There are no loads, no direct loads, it's indirect loading. Yes, tell me step by step how to do this.
Find elongations first.
One at a time. Yes, yes.
First find the elongations and then
Elongation.
sorry,
You have to speak very clearly.
change in length.
Find the free change in length
Yes.
for each element, which is L alpha delta T. Then what?
And then fixed
Then?
end fixed end forces for this. Fixed end forces.
Yeah, but it's more right to say this structure is kinematically indeterminate. So the primary structure is one in which all the degrees of freedom are restrained, and so in the restrained structure, if you allow this temperature change to take place, you will end up with what kind of forces?
Compressive.
Obviously tension, because if you take any element, it wants to shrink, it is prevented from shrinking, you will get tension, right? Right. Will you get bending moments and shear forces? Not in the primary structure, not in the primary structure, right? But in the final structure you should get. So you will be in for a lot of interesting results, so let us look at it slowly. So first, as you rightly said, we will find the fixed end forces in the primary structure, and that is simply the axial stiffness Ki, NIF is Ki into E naught I, right? We put a minus sign in general because normally you have a rise in temperature and E naught is an extension, right? But in this case E naught will turn negative, so when you substitute the results you should get a tension, right? Now it is interesting that Ki is Ea by L and E naught I is L alpha delta T. L cancels out. It's interesting, am I right? So for all the three elements you will get the same axial force. Yes or no? That is what logic says, you get the same axial force for all the three elements, right? Can you work out how much that force is? It a small force or a big force? Plug in those values. Okay, let us go back to the, so you have all the members have a cross section 300 by 300, so the area is 0.09 meter squared. The material has an elastic modulus of 2.5 into 10 raised to 7 kilonewton per meter squared. So with E, A and L, can you work out what that force is? That is it. E, A, alpha delta T is minus 40 degrees Celsius, you get a huge value, right?
990.
That's, so 990 is not a small value, it is a huge axial force. Do you think the final force will be so large? How much do you think it will be? See, this is what you would get if you were to arrest those degrees of freedom, prevent that cooling from manifesting, right? In the primary structure you get a huge force of 990 kilonewton. But had this structure, for example, been simply supported, what will be the force in all those members? 0. So it's actually not simply supported, it's hinged at both the ends, so there is some restraint. So can you guess what do you think in practice this 990 will reduce to? 100? Let's just hear some guesses.
10
10
or 20.
kilonewton.
10 to 20 kilonewton.
10 to 20 kilonewton. 40, 100. Okay, let's see what we get at the end. Good, your guesses are not bad. Let's see. But this is alarmingly high, but it's good to also have a check on what is that length, free length that would give it a 0 value. If you allow it to cool fully, then the extension will be L alpha T. L is 3 meters here, alpha is 11 into 10 raised to minus 6, delta T is minus 40. So you just need 1.32 mm. That's a small movement. Maybe it will be allowed to do so. So let's see. You must get a physical understanding to really understand this problem in its entirety. So these are the forces that you will get in those 3 elements if you were to arrest the degrees of freedom, right? All 3 elements will have a force of 990. How do you convert this to loads on the structure?
Find TD
How do you
matrices.
convert this to loads on the structure?
Find
What do you do?
transformation matrix first. Transformation
Well,
matrix.
to figure out what will be the loads, it's not easy, so you need help. And what's the best thing you can do? Use the transformation matrix. What transformation? Okay, so first we'll write the fixed end force vector. There are 6 degrees of freedom, of which only the axial degree of freedom will have a non-zero value. There is no shear force and bending moment. So we write it as minus 990 is what you will get at F1 star F, right? And plus 990 is what you will write at F4 star F. Is it clear? So this is the same for all the 3 elements. Now what do you do? Right, you do that. You have to sum it up for all the 3 elements, right? For each element you have to do the transpose of TdA and TdR, and if you expand it you can write it like this because the F star F is the same for all the 3 elements. So you just have to add the TD matrices. You do that, and this is something we calculated in the last problem, so I am picking up those values from the previous problem, and if you plug it in you will get the answers. Okay, you will get FFA and FFR, and this is beautiful. Only matrix methods does it so efficiently. If you had to do it manually, figuring out what are those equivalent forces is going to be tricky. So this is the power of the contra-gradient principle, how effortlessly from the actual force in the restraint structure you are getting equivalent joint loads. It is beautiful, very powerful. And so you can find the resultant loads, which is Fa minus FFA. Fa is a null vector because this structure has no direct loads acting on it, and so this is what you get. Okay, this is what you get, right? So it's as though someone is pressing down those corners B and C, and you can visually it makes sense. That's what's going to happen when it wants to cool, and it's supposed to, and those loads are not small, they are huge loads, 792, 396. Is it clear? How do we proceed from here? Okay,
K
so
matrix.
we use these equations, right? You solve the equations, the Ka matrix you've already got, and you look at the answers. If you plot them, it's going to look like this. Okay, B is going to go down by 3 mm, C is going to go down by 2.55 mm, and BC is going to shrink, move inwards. B goes to the right by 0.36 mm, C goes to the left by 0.96 mm. Okay, now if you are an intelligent engineer, what will you calculate first to figure out whether your residual force will be large or not?
displacement we got.
Yeah, we calculated E naught 2
Yes, sir.
was 1.32 mm or something, right?
Yes, sir.
Now,
Subtract from it and you see the
Huh?
value. Subtract from it and see the
yeah,
value.
subtract from it. What do you think you'll get?
Negligible.
So let's just look at element 2, E naught 2 for example. You can do for E naught 1 and 3 as well, but let's just take the second element because it's nicely horizontal. So E naught 2 was 1.32 mm, and if you want to find the final elongation, which you can get from d4 minus d1, right, because d4 is a horizontal deflection at C, d1 is a horizontal deflection at B, that must be the elongation in second element BC. It turns out to be very, very close to E naught 1, right. So close that if you work out, you know, you can find the actual stiffness of that element, EA by L of the element, multiplied by that and add the fixed end force plus 990 minus 989.1. Ladies and gentlemen, the force is less than 1 kilonewton. This is really beautiful, right? Really beautiful. Just 0.9 kilonewton is the force that you get, not 20 kilonewton, not 40 kilonewton, not 100 kilonewton, not 990 kilonewton. So at the end of the day, you will find that thanks to this analysis, you can confidently say, I do not need to worry about temperature changes for a frame like this. But you would not be able to say it with that degree of confidence unless you could analyze the structure and interpret the results. Is it clear? So it is not enough just to blindly use matrix analysis. As an engineer, it is more important to interpret the results. So 0.9 kilonewton is nothing for a structure of this magnitude, but 990 kilonewton is shockingly large. Okay, so why is it so low? Can you tell me?
Because AB and
Yeah,
CD
the
are.
structure will adjust itself, and you know that had D been a roller support, it would have nicely moved around a little bit, so that nothing happens. You get that 1.3200000 exactly. So the structure adjusts itself. So there is nothing much to worry in a system like this. A similar situation you will get in buildings where you have differential movements in beams. Typically in a multi-storied building, let's say you have columns and shear walls. The shear walls are quite stiff actually because the cross-sectional areas are large. The columns are comparatively more actually flexible. So when you have a huge beam sitting on top of them, where you have the shear wall you will not get much movement, where you have the column you will get a movement, and that movement gets enhanced with time because in concrete we have a phenomenon called creep. So you have differential settlement in that beam, and if the beam is not long, 6 Ci by L squared is the kind of fixed end moment that you will get. That is a huge moment. If you work out, it is very large, but when you do the frame analysis, you will find you will end up with much smaller moment. But unless you can do that distribution through an analysis, you can't prima facie say whether it is negligible or not. So when you have more members coming into play and more flexibility in the structure, you really do not have to worry too much about indirect loading. It kind of takes care of itself. So let us finish this problem. The next step is, here you find is negligibly small, and you find out the support reactions. The support reactions also turn out to be very small, not surprisingly, and it's self-equilibrating. Look at that. Okay, there is no load on the structure, you cooled the structure and you got support reactions. It's just self-equilibrating. There's no external direct loading acting on the structure. You can find the membrane forces. You get now you get shear forces and bending moments in addition to axial forces, but they are of small magnitude. You see that value which we got 0.9 for the second element, the exact answer is 0.86, which is close to 0.9. So, and these are your final diagrams. You have got your axial force diagram, shear force diagram, and bending moment diagram. The axial force diagram is more critical among these, and you will find that they are very small. Okay, so this simple problem teaches us many things and shows us the power of matrix analysis. So now with this we finished the conventional stiffness method. Yeah.
A and D are at the same level, then here the force at vertical force at A and vertical force at D creates a moment, no sir?
Yeah.
And it is balanced by horizontal force. If
Right.
it is at the same level, which will balance it, sir?
If it's, that's a good question. It's a very good question. Supposing you had a symmetric frame. Let's say you had a symmetric frame and A and D were at the same level. What do you think will happen? You can't have a vertical reaction. Why can't you have a vertical reaction? Because they have to be equal and opposite, they will create a couple. So the moral of the story is you can't have a vertical reaction, but you still can have a horizontal reaction.
So the member must be in tension, right? Tension or compression now.
Still be in tension.
Then
Can
if
can
member
you
is
take
inclined,
a frame and apply a horizontal reaction? You can have a horizontal. You understand? So there is always an answer to any question. It should make sense. Of course, one answer is the horizontal reaction is 0, but you know that is not going to happen because it is an over rigid system, it is statically indeterminate, there have to be internal forces, there have to be support reactions, but the reactions will cancel out. Is it clear? Good question. Okay, so are you now confident of dealing with conventional stiffness method? So we have completed the conventional stiffness, we have done all kinds of problems with it. Next we go to reduced element stiffness method, then we will do flexibility method, and finally we will do space frames. With that we actually cover most of structural analysis. We have a 7th module which we will take a look at. Thank you.